Hi, my name is Ariel Murphy, and I'm a senior at the University of Alabama, where I'm majoring in metallurgical and materials engineering. I am here this summer at the University of Michigan participating in the SRP program with Dr. John Allison. My project this summer involved understanding how precipitation morphology, size, and distribution of the magnesium alloy AZ91 affected its mechanical properties. AZ91 is a magnesium alloy consisting of 9% aluminum and 1% zinc. Most recently, magnesium alloys have received a lot of attention because they're lightweight. They have the potential to have a high strength to weight ratio. They have a low density, which is about 2/3 that of aluminum, but they still have some disadvantages as far as the strength is not as strong as materials that are currently being used in industry today. They have a low corrosion resistance and burn resistance. So a big part of understanding mechanical properties and properties of materials is understanding the microstructure of the material. So my project this summer involved doing different heat treatments to understand how it affected the microstructure and how that in return affected the properties. So in this diagram, all of my samples were heat treated using the ASM T6 method. In this method, the materials are solution treated at 413 degrees Celsius for 20 hours to produce a refined microstructure consisting of alpha magnesium. Then the samples are quenched in water at room temperature to precipitate out the constituents. Then finally, the samples are aged at 168 degrees Celsius at different times to allow the beta phase precipitates to nucleate and fall out of solution. So the aging time is what was different in my project. I aged at an hour, 3 hour, 5 hour, 10 hour, and 50 hours to see how that changed the precipitation microstructure. So the precipitates in the AZ91 alloy grow either discontinuously or continuously. Discontinuous growth is alternating plates of alpha magnesium and the beta phase. And the beta phase is magnesium 17, aluminum 12. And usually they grow along the grain boundaries and they're large, they're easy to see even in optical microscopy. And then the continuous precipitates are much smaller and they grow within the grains, and they are also the magnesium 17, aluminum 12 compounds. So what I did was, after I did all of my heat treatments, I looked at I characterized the precipitates using optical microscopy, SEM, and then I looked at the mechanical properties using micro hardness and tensile strength testing. So if you go to this slide, you can see the microstructure of the 1 hour sample. So you can see that there's a small amount of discontinuous precipitates in both the 1 hour and 3 hour sample, but there are more discontinuous precipitates in the 3 hour sample. If you look at the bottom 1 hour sample, you can see that the discontinuous growth, as I said before, are alternating plates of the alpha magnesium phase and the magnesium 17 aluminum 12 phase. And you can also see a small amount of continuous precipitates in the 1 hour sample. You can also see more of them in the 3 hour sample. So now I was able to see just from 1 hour and 3 hour that there was an increase in both discontinuous and continuous precipitates in both samples. So then I looked at the 5 hour and 50 hour samples. And again, you can see that the discontinuous precipitates are much larger in the 5 hour sample, and there's more continuous precipitates than there were before in both the 1 hour and 3 hour sample. And then I looked at the 50 hour sample, and you can see that the discontinuous precipitates and the continuous precipitates are the greatest amount in this sample. So that was it for SEM testing. Then I did hardness and tensile testing, and with the hardness testing, I took 8 to 10 points along the cross section of the sample, and I was looking to see if there was any difference between the hardness on the surface of the sample or in the center of the sample, just because some papers have found that there are more precipitates on the surface, which is why the hardness is higher at the surface. But for my samples, the hardness varied from surface to center, so I couldn't make a conclusion on that. But what I did find was that the hardness did increase with aging time. So I saw that hardness did increase, so the precipitation microstructure did have an effect on the hardness. Then I did tensile strength testing on the 168 Celsius aging temperature and the aging time of 50 hours. And the average tensile strength was about 213 megapascals, which is much lower than the ASM expected value of 275 megapascals. So I think the difference in that was that misalignment during testing is probably why the values were so low. But even though I wasn't able to do hardness testing on all of the samples, because strength and hardness have a direct relationship, if the hardness is increasing with aging time, then the strength also should be increasing with aging time. Then I just, after my project was done, I concluded, and I did find that both discontinuous and continuous precipitates did increase with aging time. Also, I found that I did microstructure analysis of the tensile tested specimen and found that there was no twinning, so plastic deformation probably occurred due to dislocation slip. In future work, I would like to look at these microstructures under a TEM so that I could see the orientation difference in atoms, and that could help me identify whether it was twinning or dislocation slip. And also in future work, I would like to perform XRD so I could quantitatively identify how much of the beta phase precipitates increased in the samples with aging time. So that was my project this summer. I would like to thank, the SRP program and Mike Nazareth and everybody in his office for allowing me this opportunity. Thank you.